Welcome guys, welcome to today's lecture. Now today we are concerned about boundary conditions. In our previous discussion we have discussed about boundary conditions between two dielectric surface, and now in this discussion we have to discuss about the rest, that is a boundary between a conductor and dielectric and a boundary between conductor and free space. Now if you are new to this discussion, you can check the description. There lies the link of the previous discussion. I request you to go through that one before this discussion. Now in our previous discussion we have used these two equations. The first one, E dot dl equals to 0, and the second one is Gauss's law in dielectrics. Now using those two equations we have found for dielectric interface these four equations. These four equations are our boundary conditions for a dielectric boundary. And now in this lecture we are concerned about conductor-dielectric boundary conditions. Now before I further proceed, if you are new to my channel, then please subscribe to my channel, and of course don't forget to turn on the notification bell to get the regular updates. Okay, let's proceed to our discussion now. For this we have a diagram. Now see, this purple side is a conductor and the upper side is a dielectric of permittivity epsilon. We have drawn a rectangle. By this rectangle we are to find the boundary conditions for the transverse components, and as you have seen in our previous discussion that for the normal components we shall use our Gaussian pillbox. Okay, now as we have done before, we are to decompose our E vector and D vector in transverse component and normal component. Since these mediums are different, we are not using any one or two type of notations, because in our previous discussion it was two dielectric. Okay, that's why we have used one to these notations, but here no need of that notation. Now let's use this one equation first for this A, B, C, D, A path. But before, here you see E equals to 0. We all know that for a conductor the field E field is equals to 0 within the conductor. Okay, now we have to remember this, because for this and the entire boundary conditions for the dielectric case will be transferred to this condition. Now we are starting from this A. Now for this AB path we have ET and dW. Now for the upper half of BC we have EN and dH by 2 and a plus sign. Now for the lower half of BC, what is the electric field within the conductor? That is 0. So plus 0 into dH by 2. Now from C to D the direction is just opposite to the A to B. So it is minus 0 into dW. Now for the lower half of dA, it is again 0 with a minus sign and 0 into dH by 2. Now for the upper half of dA, it is not 0 but the negative sign remains because it is the exact opposite direction of the upper half of BC. So for the upper half of DA, minus En into dH by 2, and thus our path is closed now from A to A. See, we have Et is equals to 0. From the above, it is very easy calculation, as you have know that En and En cancels out and these are all 0. So we have Et dW is equals to 0. As dW is not equals to 0, we must have Et is equals to 0. So it is our first boundary condition for conductor dielectric case. Now let's proceed to our next conditions. Now as we know that D equals to epsilon E, from this equation we can put this one into this one, that is dt is equals to epsilon Et is equals to 0. Since epsilon is not equals to 0, then obviously dt will be 0 because Et is equals to 0. So 0 into a non-zero quantity is always a 0. So we have already gained our two boundary conditions, that both the transverse components are 0 at the boundary. Now we shall proceed for the normal components. So we have our Gaussian pillbox, and as you guys know that we only take this surface and this surface for the calculations, because it is the characteristics of the Gaussian pillbox that this dH is very much small, so it can be neglected. Okay, now we have our second equation, that is closed surface integral d dot ds equals to q enclosed. It is the Gauss's law in dielectric. Now let us apply this equation for this Gaussian pillbox. Now for this surface, it is dn, n for normal, dot n cap, which is the normal as you are seeing here, n cap, dot n cap ds. Okay, now for the lower part, as we know that it is within the conductor, and within the conductor E is equals to 0, so D is also equals to 0. So we have 0 into ds. And what is q enclosed? That is sigma into ds, where sigma is the surface charge density. So we can conclude that dn dot n cap is equals to sigma. It is the third boundary condition. And if we put d is equal to epsilon E equation in this, then we have En dot n cap is equal to sigma by epsilon, because when you put this into this, we have epsilon En dot n cap is equal to sigma. So we are just rearranging the equation as En dot n cap is equal to sigma by epsilon. Now see, we have our four equations, the first one, second one, third one and fourth one. So summing it up, we can write like this. This is our boundary conditions for dielectric-dielectric interface, and this is our boundary conditions for conductor-dielectric interface. Now we can proceed in our last step, that is our third step, that is conductor free space boundary condition. Now for this we obviously need a diagram. So this is our diagram, this is free space with permittivity epsilon naught, and this is our conductor within which the E is equals to 0. See, we have already decomposed our fields E and D in their component terms. See, this is Et, this is En, this is dt, this is dn. Okay, now this case is very much easy. Why? Because it is a special case of conductor dielectric boundary condition. Why so special? Because free space is a special case of dielectric case where epsilon is epsilon naught. Just replace epsilon with an epsilon naught, the space become a free space from a dielectric space. Okay, so we can just rewrite our equations keeping the fact that whenever we get a epsilon, we shall replace it with a epsilon naught. So the boundary conditions can be rewritten for this conductor free space boundary as these two. Actually it is not two equations, it is four equations. See, dt is equal to epsilon naught Et is equals to 0. It means dt is equals to 0 and obviously Et also equals to 0. It is identical to these two. And now for the rest of the two, dn dot n cap is equal to epsilon naught en dot n cap is equals to sigma. Now see, this thing is also unchanged. What has been changed here? This sigma, this epsilon, it has been converted to epsilon naught. So what will be our last condition? Can be rearranged as en dot n cap equal to sigma by epsilon naught. Okay, so see, we have already found our most important boundary conditions for the three cases. This one is for dielectric case. It is the most important for your mathematical treatment. These equations are for dielectric conductor interface. It is also very important, and to some extent less important are these conditions. Actually these conditions are direct derivation of these. Okay, so these two set of equations are very much important for your mathematical purpose. So guys, this is the end of our discussion today. If you like my video, then please like, comment and share my video. And thank you guys for watching. See you soon.